So I wasn't able to finish the whole section 4.1 in last video. So this is the fourth video for section 4.1, and we have two examples to cover, and this one was a very long one, so I did half of it already. So we'll go through each step of this, and then we will do the rest of the axioms as we go. So it says let B be a set with of 2 by 2 matrices, which are depicted here. So A, B, C, any real number, and the fourth place there is 1 always. So if you have a matrix where A, B, C are real numbers, and you have a 2 here in the place of 1, then that is not in this set. Or a 3 or any other number. So 1 is just going to stay 1, then will be a vector space. So it says if addition and scalar multiplication are the standard component wise operation, show that V is not a vector space. So if you notice that if we have a normal, our standard addition, so I will have A, B, C, D, no, A, B, C, 1 plus D, E, F, 1 will give us A plus D, B plus E, C plus F, and here I will get 1 plus 1, 2. Is not, or do we make this sign and then cross it into V. So this does not belong to V, so V is not closed under addition, so therefore it is not a vector space. And so V is not closed with respect to addition. That's why it's not a vector space. Now, but B part says define A, B, C, 1 plus, so special plus sign, D, E, F, 1 is A plus D, B plus E, C plus F. So this part is similar to what we had in the standard one. This last quantity is 1. So if this 1 stays 1, the other entries they change. So now we have to show that this is a vector space. Okay, let's see. It's a long one, but we will start. So 1 and 6. I'm writing here 1 and 6 are true from the definition. So if we are given this definition that this is how addition is going to work, and this is how the multiplication is going to work, so we can see that we already have this in the definition, that because the sum of these two is this, so it must be in the set. And similarly multiplying by k, you get that vector, and that is already in the our set V. So we start with basically number 2, where we have to show commutation, like first vector plus second vector is the same as second vector plus first vector. So I took the first one as A1, B1, C1, and fourth place is 1. Second vector A2, B2, C2, fourth place is 1. When we add them by using this defined addition, we get A1 plus A2, B1 plus B2, C1 plus C2, and 1 remains 1. Now you can now go to the next line and do A2. So A2, you switch these two, and then you can go, or you can go as I did from here to here, because these are real numbers inside the matrix. So A1 plus A2 it can be written as A2 plus A1. Similarly, C1 plus C2 can be written as C2 plus C1. And similarly, B1 plus B2 can be written as b2 plus b2 plus b1, which can be thought of as this came from the addition of a2 b2 c2 1 plus a1 b1 c1 1. So this shows the commutative property that this vector a plus v1 plus v2 is equal to v2 plus v1. The third property, the associativity. So we have one vector here, and first we add these two in the parentheses. First we add these two in the parentheses, which will give me a2 plus a3. I'm coming down here. What we are checking is this statement. This vector plus parentheses, the sum of these two, this and this, is equal to, now I have the first two combined first and then add the third one. So we check left hand side will be a1 a b1 c1 1, and these two get added, which we show here, and then we add the first to this result and we get that result. So the right hand side, first we add the first two, so a1 plus a2, b1 plus b2, c1 plus c2 1 plus a3 b3 c3 1, which will give us this. So now you see left hand side equal to right hand side. So yes, this is satisfied. Number 4 is the identity. So we need to find an identity. So we can, just by observation or by looking, we can tell that the identity would be 0, 0, 0, 1, because we can show that if we have a vector or this 2 by 2 matrix A, B, C, 1, according to our addition, we find, if I add the identity which we have kind of alleged that this is going to be the identity, we look by adding a vector to the identity or adding the identity to a vector, and we see that we get back our vector. Similarly, the inverse of any vector or any matrix A, B, C, 1 will be negative A, negative B, negative C, 1. Why? Because if you add this inverse to the actual vector, then the sum will give you the identity. That is the definition of the inverse. That when you combine or add the inverse to its actual vector, then the sum must be identity. Okay, so these are the 5 axioms. 6th one I already mentioned, it's with the definition. So 7th is for scalars. Let's say K and M. Scalars K and M plus K into A, B, C, 1. We want to see that is this equal to, I forgot the multiplication sign. We have K plus M multiplied by A, B, C, 1. Is this the same as K this is what we want to figure out, this left hand side and right hand side, are they the same? So left hand side is going to look like, by definition, a plus m, a plus m b, a plus m c, 1. I can distribute here inside and we get ka plus km plus ma, and here I get kb plus mb, kc plus mc, and 1. I'll leave it here and we'll look at the right hand side. The right hand side will be first ka, ke, kc 1 plus ma, mb, mc1, which will give us ka plus kb, plus ma, ka plus ma and then here kb plus mb, kc plus mc1. You notice that these two are same. We say left hand side equal to right hand side. So that is checked. Now number 8 is that you have k as a scalar, and if we have two vectors inside a1, b1, c1, 1 plus, so we have another vector a2, b2, c2, 1. So the axiom says that if you have this situation, then it should give you the same answer as if you have this one. K times a1, b1, c1, 1 plus k times a2, b2, c2, 1. So these are two different vectors with one constant. So we again look at it with a left hand side and right hand side. The left hand side will give me k. We first add the vectors. Then becomes k into a1 plus a2, k into b1 plus b2, k into c1 plus c2, and 1. So I can now distribute the ka1 plus ka2, kb1 plus kb2, kc1 plus kc2, 1. And I can leave it there and look at the right hand side, or I can just write it as, this can be written as, we can split it. I think we should go with the right hand side. I need another page here. We look at the right hand side now. So first we are getting k times the first vector, so which is k1, k b1, k c1, 1 plus ka2, kb2, kc2, 1, and when we add, we get ka1 plus ka2, kb1 plus kb2, kc1 plus kc2, and 1, which is the same as the right hand side, left hand side. So this is done. Now the next one is, I think it's number 9 or number 9. 9 is that if you have two scalars, k and m, does this work, k times m times abc 1. We are going to check, does this give us the same answer as km times the abc 1. The left hand side will give me k ma mb mc 0, not 0, sorry, 1, which is then going to give me k mb ma k mb k mc 1, which is just kma kma kmb kmc. And look at the right hand side, that is km kma kmb kmc, and 1. So this is the same as left hand side. This is satisfied. Now the last one, number 10, is 1 into notice it will give us a b c 1. So this is also true. Hence B is a vector space. It's very long problem. Okay, so one more example here. This says let S be the set of all polynomials of degree less than or equal to 2. Less than or equal to 2. So it's saying, is this set S, will it be a subspace of P4? What is P4? It is a space of all polynomials of degree less than or equal to 4. So P4 has elements like a naught sub 0 plus a1x plus a2x squared plus a3x cubed plus a4x 4. So 4 degree, everything of 4 degree or 3 degree or 2 degree or 1 degree or 0 degree. So those are all in the at P4. But in P2, or this set S, we have the elements are, or the vectors in S are of the form a sub 0 plus a sub 1x plus a2 x squared maximum. So we know that 0 can be written as 0 plus 0x plus 0x squared. So it is in S. 2 should take 2 if px equal to a sub 0 plus a1x plus a2x squared, and qx is equal to b naught plus b1x plus b2x squared, and px plus qx will be, we already know the constants will add up, so a sub 0 plus b sub 0 plus a1 plus b1x plus a2 plus b2 x squared. Which is belongs to S. Why? Because these are real numbers. Now if we have got constant or scalar, this is the third for scalar, MP is going to be m a sub 0 plus m a sub 1x plus m a sub 2x, which is also going to be in, this belongs to S. Hence, S is a subspace of P4. So this is it. I hope you guys can do the problems now.